In this video, we're going to take a look at the refraction of light, the bending of light as it goes from one material to another, and we'll look at it through the lens of Snell's law, which describes that bending. So let's say we have a surface and it separates some substance 1 from another substance 2. This could be air, and this could be water or glass or some kind of mineral of some sort. As light comes in, when it hits this substance here, it might not necessarily travel through that substance in a straight line. Instead, it is likely to be bent unless light travels with the same velocity in both materials. And so it's that bending of light that we refer to as refraction. Now, refraction is dependent on velocities, so we have to talk a little bit about the velocity of light. So the velocity of light, we often know from this equation here, E is equal to mc squared, where c is the speed of light, m is mass, e is energy, and for our purposes, we don't care about that part. So c is the speed of light, but not just the velocity of light anywhere, but here it's the speed of light in a vacuum. So when there's no mass for it to travel through. And that speed of light is a constant at 300,000 kilometers per second. It is also an upper speed limit. Nothing can travel faster than the speed of light in a vacuum. But light can actually travel at slower speeds. And we're going to take a look. Let's clear the chalkboard. We're going to take a look at something referred to as the index of refraction. And the index of refraction is noted by the letter n. And so the letter n gets this value. It is the velocity of light in a vacuum divided by the velocity of light in some medium. And if we wanted to, we could put a little superscript here just to note that this index of refraction belongs to this thing down in the numerator. Now, what's the medium? Glass, air, water, calcite, quartz, doesn't really matter. Let's let it be air. So the index refraction for air would be the velocity of light in a vacuum divided by the velocity of light in air. And it ends up that this value is very close to 1. It's 1.000274 or thereabouts. There are no units on it because we're dividing units of velocity by velocity, so the units would cancel out. But because it's so close to 1, you could see that these velocities are very close to one another. So the velocity of air is almost the same as a vacuum. Also note that this ratio can never be less than 1. This ratio, whatever it is always going to be greater than 1. We can take something that is so-called rarefied, like air, something that has a very, very low density, and the value will approach 1, but it always must be greater because the velocity of light in a vacuum will always be greater than the velocity of light in any medium if we accept Einstein's idea that the 300,000 kilometers per second value is an upper speed limit for light and, well, for pretty much anything else. So how does this work for mineralogy? We can use Snell's law. So here is Snell's law. Again, we'll take some flat surface, and let's say it represents separation of air and then some mineral. It doesn't matter what it is, we'll just call it mineral. So light is going to travel from air into a mineral. Let's have a vertical line as reference, and we'll have light coming in at some angle. So here's an incoming ray, and we'll call this angle I. That'll be the angle of incidence. And then that light is not going to come straight through. It will allow it to be bent, and so we'll draw it at a somewhat steeper angle, though it could be more shallow, and we'll call that R. That is the angle of refraction. So the angle of refraction is R. That's an F right there. So Snell's law tells us that the sine of I, of angle I, divided by the sine of R would be equal to the value for the index of refraction of the mineral divided by the index of refraction of air. So sine I over R is basically this fellow over here. That comes up as the numerator. Let's just call this N2 because that's the way it's usually written. So we'll call this N2, and this one is N1. We usually write this as N1 over N2 over N1. So that's the way the Snell's law is usually taken. But if we're interested in the velocity of light in a mineral, and we know that the value for air is close to 1, then that one drops out. Let's erase the chalkboard and just replace and rewrite that equation again. So Snell's law tells us that the sine of I over the sine of R is equal to N2 divided by N1. In that previous slide, we said that N1 is equal to air, and the value for air is equal to 1. So this is just equal to N2, where N2 is whatever mineral or glass or any other object that transmits light. That's the thing that we're interested in. And this is essentially 1 over the velocity of light in that material. So when we think about indices of refraction, they are essentially the inverse of velocity. And the inverse of velocity then would be this index of refraction. So index of refraction is going to be essentially equal to, when it's listed, when it's, you see numerical values in the table, it's that value of n will be the velocity of light in a vacuum, which is going to be very close to the velocity of light in air, divided by the velocity of light in whatever the material is. And we'll just write MIN for a mineral, since that's mostly what we'll be looking at.